Hey everybody, welcome to the second part of today's talk. So we have our own Junaid Razzaq, who will talk about, from Charles University, who will talk about complex structures for the full flag manifold quantum SU3.
Hello everyone. Thank you for being here, and special thanks to the organizers for giving me this opportunity to speak. I will be talking about complex structures for the full flag manifold of quantum SU3. This is a joint work with Ramon and Alessandro. Okay, so the topic looks a bit very specific to some very particular situation, but I will not directly go to this. I will start from very basic things, and then at the end I will talk about this topic. And of course, whatever I am gonna say, I think many of you already know these things very well. So especially Ramon. So fortunately, he's here. So if I say something incorrect, uh, he will definitely correct me. Okay, so I will start from the very basic things. I mean, what are quantum flag manifolds, and then what have been done, and then what is this work about? Okay. Okay, so classically, what is a flag manifold? So if we have, let's say, a complex vector space, n-dimensional complex vector space, and then we fix, sorry, uh, it, I mean, the angle is, I don't think, so I think it is correct if I use this. It's working, but the angle, I mean, doesn't seem to be very compatible. Okay, so so we fix some numbers, distinct numbers from in an increasing order between 0 to n. And then we consider a sequence of subspaces in V, let's say V1 contained in V2, I mean up to so on Vn, Vk, such that dimension of each of these Vi, Va is equal to the numbers that we have fixed, Ia. Such a sequence, we call it a flag. And if you fix a flag with this signature, what you have already fixed, and if we collect all these sequences of a fixed signature, we call it a flag manifold. For the moment, don't worry about the word manifold. We will see. There are many ways to consider them as manifolds, but we will see in a moment. An interesting first example is the notion of projective space, which is by definition the collection of all one-dimensional spaces in Cn, so all lines. The next one, so just a small extension of projective space. So here we consider one-dimensional, but if you consider any m-dimensional space subspaces of Cn, then we call it Grassmannian. And then another interesting, class is what we call full flag manifold. So these are, this is a flag manifold whose signature is 0, 1 up to n. So we actually take all the possible, numbers 0, 1, 2, 3 up to n, and then this is, the next extreme to the case of Grassmannians. Okay, so and then, of course, you can talk in between. These are partial flag manifolds. Now, we know that if you look at SUN, then it acts transitively on Cn, in particular also on this complex projective space via matrix multiplication. And if we fix a base point, let's say 1, 0, 0, the first one, then the stabilizer of this point is going to be S of U1 times UN minus 1. So, these are going to be all the matrices in SUN, which looks like this. Here you have some complex number and 0, here you have zeros, and here you have another. So here you have a copy of U1, and here you have a copy of UN minus 1. So by orbit stabilizer theorem, you can consider complex projective space as a quotient of SUN modulo this stabilizer. So similarly, if you understand this one, then the next things are the same. With the same logic, we can consider Grassmannians as homogeneous spaces of SUN with the same logic. Okay, so now, so with these identifications, we can consider flag manifolds as, let's say, real analytic manifolds as homogeneous spaces of SUN. Why I am taking these identifications? Because we want to define what we call quantum flag manifolds. So we will use this picture. Okay, so this is all what I want to say about classical situation, and now I want to go towards the quantum situation. So the idea is to deform these spaces. By that, what we mean is to deform their algebra of functions. For this, we have to use the notion of Hopf algebras and quantum groups, and I will quickly go through these things. So what is a Hopf algebra? I'm sure all of you know this thing. So it is a unital associative algebra together with two maps, which one of them is a covariant of product, the other one is a covariant of unit, which we call co-product and co-unit respectively. And then we also need another map S from A to A, which is an algebra antimorphism. We call it antipode, or sometimes we call it co-inverse, such that these properties are satisfied. So this is the first property is just the covariant of associativity. The second one is the co-unit condition, and the third one is what makes S an antipode. Okay, so for us, why it is interesting is the following. If we have any, okay, so for this example, I consider algebraic group. If we have any algebraic group and we denote by O of G the coordinate ring of my group, then together with pointwise addition and multiplication, this of course turns into an algebra. But if you look here, you are not using the group structure of G. So to capture the group structure, we actually need to put the Hopf algebra structure. So we define co-product, co-unit, and antipode as follows. So delta of F is gonna be, so it is gonna be a function on G times G. So at any tuple G prime, it just gives you F of G times G prime. So here you can see that the co-product is somehow capturing the multiplication inside your group. Similarly, the co-unit of F is gonna be F of E. So co-unit is capturing the identity of your group. Similarly, the co-inverse, which is S, is capturing the inverse, the information of inverse inside your group. So together with this structure, our O of G turns into a Hopf algebra. Okay, so this is a commutative Hopf algebra corresponding to an algebraic group. So whenever we say that we have a quantum group, what we do is most of the time we deform this algebra into something non-commutative, but we try to keep the co-product and co-unit and antipode very similar thing. Okay, so let's try to deform what we need. We need to deform the algebra of functions on SUN, right? So for this, we have to go through some basic things. So if we have any non-zero complex number and nu, let me define it to be q minus q inverse, then we define the algebra of quantum matrices, which we denote by this thing. It is an algebra generated by uij's, and then we take the quotient by these relations. So you can see if I put q is equal to 1, we recover back the algebra of polynomials on our n by n matrices. And this algebra of quantum matrices turns into a bi-algebra. I mean, it admits a co-product and co-unit, which is in fact, you can see easily, it is given by matrix multiplication and the identity of matrices, let's say. And then we want to turn it into a Hopf algebra. For this, we also need to have inverses. So let's define what we call quantum determinant. This is just a deformed version of the notion of determinant. And then if we fix this determinant to be equal to 1, I mean, roughly speaking, then what we get is something that we call quantum special linear group. And together with this co-inverse, this quantum special linear group turns into a Hopf algebra. If you look at it, it is exactly giving you, if you consider A to be equal to uij, then in fact, so S of uij is exactly the entries of A inverse, roughly speaking. Okay. So now we have defined a quantum special linear group, but we need a real group, which is SUN. For this, we need a star structure. So if we take, this is going to be a star structure, and if we take this together with our quantum special linear group, we call it quantum special unitary group. So like the classical case that we can realize SUN as a real form of SLN. So here it is the same thing. Okay, we have, we have defined something as quantum special unitary group. We also need something like Lie algebra of special unitary group. For this, we have to deform the Lie algebra of special unitary group. Let's see how we do it. For any Lie algebra, we can define its universal enveloping algebra, and then we can turn it into a Hopf algebra together with this structure. And then if we have actually a semi-simple Lie algebra, finite dimensional semi-simple Lie algebra, there is this very celebrated construction by Drinfeld-Jimbo, which gives us, an algebra which is going to be a Hopf algebra in next slide, which is very similar to the our previous case. So we defined here for any Lie algebra, its universal enveloping algebra is actually Hopf algebra with this structure, and we will deform this structure somehow to get Hopf algebra structure on this Drinfeld-Jimbo quantized enveloping algebra. So here it is. So if you somehow skip ki's or set them equal to 1, you will see that you recover your universal enveloping algebra. And if Q is a real number, then this UQG admits a star structure given by this thing. And if we consider UQSLN together with this star structure, we call it the quantum enveloping algebra of SUN. Okay, so we have deformed special unitary group. We have deformed its somehow corresponding Lie algebra. And now we want to see how they talk to each other. For this, we have this notion of dual pairing of Hopf algebras. So which is, if we have any two Hopf algebras, then we say that we have a dual pairing, which is a map from G tensor H to C satisfying these properties. And what we are interested in is the following. So OQSLN together with UQSLN, we have this dual pairing of Hopf algebras where you can easily somehow see what is happening here. And then this pairing also respects the star structure on both of these things. So we can also consider this pairing to be a pairing of OQSUN and UQSUN. By this I mean, I don't write what do I mean by, I mean it is respecting the star structure. So by respecting the star structure, I mean that G star H should be equal to G S of H star bar. And similarly, if you have star here and G is here, so they behave nicely with respect to the star structure. Okay, so we have deformed quantum special unitary group and its corresponding Lie algebra, and now we are almost prepared to define what we call actually A series quantum flag manifold. So if we have S any proper subset of simple roots in the root system of SLN, then we consider this Hopf subalgebra generated by these things. So we take all the Cartan part, and then we take only those EJs and FJs which belongs to my set S. And then we define quantum flag manifold as the subalgebra of UQLF invariants. So somehow we are taking those functions of SUN which are somehow invariant with respect to infinitesimal action of the corresponding Lie algebra. Okay, so if the complement of S in the set of simple roots is a singleton set, it means if we take all the roots except one, so we cross, then what we get is quantum Grassmannian. So for example, if we cross the first node, so like here, what was happening, so it is gonna be the corresponding Lie algebra is gonna be S of U1 direct sum with S of UN minus 1. So we cross the first node and we get quantum projective space. Similarly, for quantum Grassmannian, we have, so this one, Grassmannian 2, 4. So we have, so in the classical situation, we are gonna have OQ SU4 modulo, sorry, SU4, let's say, modulo S of U of 2 times 4 minus 2, which is again going to be 2. So we have one copy is here, one copy is here. Similarly, if we take S to be the empty set, I mean we cross all the nodes, then we get, so in our UQLS, we are only left with the Cartan part, so the corresponding flag manifold is going to be full flag manifold. Okay, so the case, okay, before I go to the next slides, so these cases accept full flag manifold, I mean these quantum projective spaces which are included in quantum Grassmannians, they have been well studied already. I will talk about these in a moment, but the other flag manifolds, they are not very much studied. So the case, for example, this one is the standard Podlar sphere, which is, I think, one of the most studied examples in non-commutative geometry. But what we are, all, for example, quantum projective spaces, this is also an example. They are, or I mean, all of them are very well studied. But for the other ones, there is not enough, I mean, literature. So we want to go beyond this setting, what people called irreducible flag manifolds. So the first non-trivial example, I mean, that we can consider is the full flag manifold OQF3, which by definition is going to be this one. And we will see some results about it. And if you just forget about the definition, so OQF3 as a subalgebra of OQSU3 is going to be given by these things. Okay, so we have defined our objects of interest, I mean, what we call as quantum flag manifolds. The next thing is what we want to study about these things. So the notion of differential calculi have already been very well explained by Giovanni. So I will quickly go through these slides. So a first order differential calculus is just a bimodule together with the differential from our algebra to this bimodule satisfying these properties. And then we know that there is a universal first order differential calculus. Everything is going to be a quotient of this differential calculus. And then what is a differential calculus? I mean, a total differential calculus. This is going to be a differential graded algebra such that the zeroth, I mean, part, the first component coincides with our algebra A. And then, as Giovanni was explaining, what do we mean by covariant differential calculus? So if we have a co-module algebra B, then we say that we have a left covariant differential calculus if it also admits an action of a coaction of our Hopf algebra, and then they behave very nicely. And then this is the result by Voronowicz, which was explained by Giovanni. But unfortunately, we are not always in this beautiful picture. So what Voronowicz is considering is the situation where B coincides with A. So Hopf algebra acting on itself. I'm not sure if it is fortunately or unfortunately that we are not always in this situation, because this situation is not always very nice. For example, there are certain quantum groups for which there doesn't exist any differential calculus of classical dimension. So I'm not sure if it is a fortunate thing or unfortunate thing. So the point is, sometimes we don't look at the Hopf algebra, but maybe some smaller part of it together with the action of the big Hopf algebra. Such things are called, I mean, this is our situation for, yes?
Think of it like classically, like the spaces are not always functions of a group, right? So if you think of the Hopf algebra corresponding to something with a group, then we can look at bundles of something with a group acting on it. But the space we are having is not always like functions of a group. That's why probably it's actually good that we can do something more simpler.
Okay. Okay, I still don't know. But okay, so in any case, so what I was saying, that we are not always in this situation. Sometimes we study things which are smaller part of a big Hopf algebra, and then we consider the action of our Hopf algebra on this smaller part. And these are called quantum homogeneous spaces. So how we define these things. So if we have a Hopf algebra surjection from one Hopf algebra A to another H, then we can view A as a right H comodular algebra together with this canonical coaction. And then we consider, with this data, we consider the space of co-invariants. And we say that it is a quantum homogeneous space if A is faithfully flat as a right module over this quantum homogeneous space. Okay, so why I'm defining it? So because our quantum flag manifolds, they are gonna be quantum homogeneous spaces. How we define those? They don't look something like this, right? For example, I defined so OQ, that's SUN, S. We define these as OQG, OQ, let's say SUN, and then we are taking the invariants, right? So it doesn't look like this, but believe me, you can put it in this form. I mean, it is not very difficult, but to give you all the details, it is going to be difficult, but I can just write what it should be. So pi is going to be a canonical surjection from OQ SU n to OQ SU n modulo. Then I have OQ SU n LS plus, whereby this I mean intersected with the kernel of the counit times OQ SU n.
Right, here, so UQLS is acting from the left, right?
Yeah.
So then you want this should be the same thing as a coaction from the dual of algebra on the right.
Yeah, that is also, yeah. Yeah.
Right, it's like joule to LS, and this projection map is joule to.
Yeah, I don't know how to explain it. So yeah. Okay, so our quantum flag manifolds are particular examples of quantum homogeneous spaces. Okay, so the point is what we have here, which is a result by Voronowicz, which is a particular situation, but thanks to Hermitian, it is Hermitian or Hermitian? Hermitian. Okay, in any case, whatever, thanks to this guy, we have actually a generalization of that picture. So if we have a quantum homogeneous space, then for any ideal inside B plus, which is what I was writing here, that B intersection with the kernel of the counit, we can define this omega 1 as A cotensor over H with B plus over I1 with this B bimodule structure and this left A coaction, and we define this differential, then this is going to be a left A covariant first order differential calculus on B. Moreover, every left covariant first order differential calculus on B is going to be of this form. So if you look at it and you try to see what Voronowicz was doing, it is actually, in the case of Voronowicz, our B is going to be equal to A, and this cotensor is going to be just a tensor, and everything will boils down to Voronowicz result. So this is exactly a generalization to the case of quantum homogeneous spaces. Yeah.
Every element is
Yeah. And I should be thankful to Thomas because he was the guy who introduced me these things. Thomas has a very beautiful notes. Okay. Then, okay, sorry, here I defined something. So we call this V1, which is B plus modulo I, as the cotangent space associated to this differential calculus. Okay, then there is another thing that if we are in this type of situation, what I wrote here, I mean the quantum flag manifolds. So we have a Hopf algebra, Hopf subalgebra, and our quantum homogeneous space look like this. Then we say that something is a quantum tangent space for B if it is a subspace, if it is a subspace of B dual such that T direct sum with complex numbers is the right co-ideal of B dual, and we have this thing. Why we define it? Because in the previous slide we saw that we can somehow construct left covariant differential calculi using ideals contained in the B plus. So if we have these quantum tangent spaces, there is a natural way to construct ideals. So the ideal is gonna be all, so for any tangent space T, the ideal is gonna be all those points of B plus which are killed by these, all the members of T. And then there is this beautiful result by Heckenberger and Kolb that there is a bijective correspondence between isomorphism classes of finite dimensional tangent spaces and finitely generated left A covariant first order differential calculi on B. And then again by the same guys, there is this very beautiful result that there exist exactly two finite dimensional left covariant first order differential calculi over the quantum Grassmannians, and the maximal prolongation of the direct sum of these two calculi have classical dimension and admits a unique covariant complex structure. So somehow you can see that in case of quantum Grassmannian, you have a unique deformation of their classical geometry. This is a very, I mean, big statement, but the point is, and then of course, due to this result, these quantum Grassmannians got a lot of attention. So there are also many other things which have been studied about quantum Grassmannians. I will just write two things. For example, quantum projective spaces admits a non-commutative Kahler structure, whatever that means. I will not explain. And then even so, there is generalization of this result that quantum Grassmannians admits a non-commutative Kahler structure as well. Okay, so Raymond.
He proved a weaker result, that it was for every value of Q except for some possibly possibly empty finite set.
Yeah, so
because the proof
there are some finitely, so you have to skip some finitely many Qs.
I hope that these Qs are, that there are no such Qs, but they're that's for the positivity of the Kähler structure, that it gives you an inner product and hence a Hilbert space.
So Junaid, maybe a very quick question about the theorem from Eggenberger and Kolb that you cite. So here, when you say that there are exactly two finite dimensional left covariant calculi on the Grassmannian, you mean the one corresponding to the holomorphic and the anti-holomorphic part of the quantum tangent space, right?
Exactly.
Okay, so you just take the sum and some prolongation is classical. Okay, thank you.
Thank you for your question.
What were you saying, Kerry?
So we get the Kähler structure.
No, for all except a possibly empty.
No, but you were okay.
For CPN, yeah.
Okay.
All Qs, yeah. can just do
CPN. Yeah. Real queues. Even for CPN, you have real queues, right? Real. Okay. So, I mean, these are just some things about quantum Grassmannians that I described. But I mean, there are many other studies that have been done for these things because they are having somehow, due to this Heckenberger curve, they have very unique kind of deformed geometry. So of course, the question is how other quantum Flag manifolds behave. Do we have some, let's say, nice differential calculi on other classes of, let's say, quantum Flag manifolds? What could be a good choice of quantum tangent space to put for putting a differential calculi? And the answer for a particular class of full flag manifolds, the idea by Ramon and Peter Somberg was this, that we try to use some Lustig's root vectors. So let me explain what these are. So if we have any complex semi-simple Lie algebra with blah, 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 then the braid group is the group generated by these, I mean S1 up to SL, where L is the rank of your Lie algebra, together with these braid relations. So I mean, it is very similar to the Weyl group, except for Weyl group we have another relation which turns it into a finite group. So you can consider it as an infinite version of Weyl group. Okay. The point is, to every generator of my braid group, there corresponds an algebra automorphism of UQ of G, where by UQ of G I mean Drinfeld-Jimbo quantized enveloping algebra corresponding to G, together with these, I mean, explicit expressions. Okay. Now, this is a classical statement that if we fix any reduced decomposition of the longest element of the Weyl group, and we have this list of simple roots, and then if we define these beta ones and then up to so on beta, all other betas with these, with the use of our fixed reduced decomposition of the longest element, we actually recovers all the positive roots of G. And now somehow the motivation is to try to mimic this thing to define something called root vectors for our quantum enveloping algebras. These are called Lustig's root vectors. So we do the same thing that the so here I defined just the positive ones. The positive Lustig's root vectors corresponds to beta r is exactly gonna be given by this thing. So we replace wi's with these ti's, where ti's are exactly these things. So corresponding to every generator of our braid group, we get automorphism of UQG, and then we can define this thing. For example, for the case of SL3, our group, Weyl group, is going to be S3. So the longest element is going to be this thing, and then it exactly admits two reduced decompositions. And corresponding to these ones, we get these two classes of Lustig's positive root vectors. Now, it is very important to note that this is actually depending on the choice of your chosen decomposition. For example, even this in this very low rank case, these two things are not gonna span the same things. I mean, if you see these two things are not same. So so the Lustig's root vectors are gonna depend on the choice of your reduced decomposition. So what Ramon and Peter Somberg did was the following, that if we consider this one, this reduced decomposition for the case of SLN, then the space spanned by positive Lustig root vectors is a quantum tangent space for OQSUN, and whose restriction to the case of quantum Grassmannians gives the anti-holomorphic Heckenberger-Kolb quantum tangent space. So somehow you can see, so this result is somehow generalizing the Heckenberger-Kolb picture to the level of OQSUN, and then we will restrict it to the full flag manifold. And furthermore, the restriction of this differential calculus to the full flag manifold has classical dimension. This is just the what we call anti-holomorphic part. And now what we did is we try to, so here we are talking about only the anti-holomorphic part. So in our work, what we did is to extend this picture for the case of SU3 to star calculus and then study the classification of complex structures. So we define so we already have this tangent space anti-holomorphic with respect, okay, sorry, I already have it given it here. So it is exactly this one. So if you look at it, so if you take this reduced decomposition, so for the case of SL3, this is this one. So we are gonna get this these Lustig's root vectors, and the space spanned by these elements, what we call anti-holomorphic quantum tangent space. And then we just use the star structure of our underlying universal enveloping algebra to extend it to a star, let's say, differential calculus. For this, we need to extend this tangent space. So these are, I mean, just some explicit computations, and then we just take our tangent space to be the direct sum of these two things. And then what we did is we try to compute the maximal prolongation of the first order differential calculus coming out of this tangent space, and we get these beautiful relations. And then I mean, if you just look at it, they looks to give you the classical dimension, and it is true. We just need to somehow straighten some things, and then we exactly have a classical somehow basis like the classical thing. So our dimension of our, I mean, exterior algebra coincides with the classical situation. So that is actually a very beautiful thing. And then the next thing is that the first order differential calculus that we consider, it admits up to identification of opposite structures, two covariant first order almost complex structures. Explicitly they are given by these things, and they extends to an integrable almost complex structure, which means so they gives us both of these things gives us complex structures on our quantum flag manifolds. So the point is, it is a bit different than the classical situation. In the classical situation, what happens is that we have 2 to the power of number of positive roots as almost complex structures. Here, in this case, they are going to be 2 to the power 3, which is going to be 8. But here in this case, we are so up to identification of opposite structure, we are going to get 4 in the classical setting. But here in this quantum setting, we are reduced to 4 almost complex structure, which means we have 2 to the power of number of simple roots, and all of these things are integrable, and so they gives us complex structure, which is again a very non-commutative thing, because in the classical situation we have some things, we have two, let's say 2 structures which are almost complex structures, but they are not complex structures. So why some of the almost classical almost complex structures fail to be almost complex structure here in the non-commutative setting is because that the action of OQSU3 on this V1 is a bit non-trivial than the classical setting. So we cannot always split. Okay, so we have, our paper is about OQF3, but then with some representation theoretic argument, Raymond actually proved that even for general n, for any n, that if we do the same thing, the differential calculus that we are going to get with this recipe, there exists up to identification of opposite structures 2 to the power of number of simple, sorry, here I don't think there should be up to identification of opposite structure. No, so there shouldn't be this statement that up to identification of opposite structure. So for the differential calculus, for any n, we have 2 to the power number of simple roots of these left covariant first order complex structures, and the conjecture is we don't know if they are integrable. So for this we have to explicitly compute what is the maximal prolongation, and we don't have it.
Extend from first order to higher.
Yeah, that is also a problem. Okay, so this is a conjecture, and that's it. Here is some references. Thank you very much.
In person or online?
Thanks for the nice talk. So the first question would be, so you said that there's a drop in the number of first order almost complex structures from the classical, where it was 2 to the power of positive roots. Now here it's 2 to the power of the simple roots. Yeah? And you mentioned a little bit why this happened, but so can you explain us a bit more? So why you think that, or why you proven that there are less?
Yeah. Okay, so
what's the reason?
We have this V1. So we want we want to split it into 2 pieces, right? So it should be a splitting of right OQSU3 modules, right? Sorry? OQF3 or OQSU3? Yes, you are right. Yeah. And then the point is, in the classical case, you can consider some splittings, but when you go to the quantum case, there are some relations. For example, let's say in this case, it is gonna be what it is. So E alpha 1 with some members, I don't remember what it is. It is gonna map to nu times E alpha 1 plus alpha 2. So this situation doesn't appear in the classical setting. So the point is, if I want to put E alpha 1 somewhere, I also have to put E alpha 1 plus alpha 2 in the same, let's say, V10 or V01. but that doesn't happen in the classical setting. They are not related. So this is the point. I'm not sure if I.
No, it's. I think I like partially understand it. Yeah. Yeah, because like you could think that quantumly you should have like more options, not less. But here I also see that, of course, your calculus is more complicated, and this is why it's very difficult to find such.
I'm not sure why.
Structures.
I'm not sure why you will expect more things in the quantum setting.
Because you should get like there's always a classical limit, right? So you expect that you have classically you should get all structures that you have from differential geometry.
Okay.
But it's also true that here you're building these structures on a complicated quantum calculus. That's the reason. Okay, and maybe as a second question, so for the Drinfeld-Jimbo quantum groups, you have an R matrix that is in the background, and so you haven't mentioned any R matrix here. Does the R matrix play any role in the linguistic group vectors or this picture, or is it just that you don't look at it?
It is, of course, it is there, but we don't use it. At least for this picture, we don't need, but of course, it is there.
Nice result. Framework where you these disclosures will be important. A year later, you can take. So you have your OR matrix, the cohort triangular structure of OQG. You can realize Lustigs root vectors. Lustigs root vectors live in UQG, which you would. But what else do you have in the you've got the L functionals coming from the OR matrix, the opposite triangular structure. And if you fix one of those, you can show that the root vectors, Lustigs root vectors, for a particular choice of reduced decomposition of the right group are the same as the L function. So there's an OR matrix realization of Lustigs root vectors, or they identify specific choice vectors. Which probably makes sense, right? Because you build something from the break group. I mean, this is a make for a break group thing. Our metrics are form as a representation of break group. So maybe it makes sense there. But that's a thing. And other times, just mind to make a comment on this. You see here that this is not a mass of zero. Because you don't have coaction, you don't have an action with coding. So the V1 is delayed in HA bar mass of zero. Like an hypermobile plus hypermobile, this is not. It always you multiply by an element flag, if it just flags and get the co-unit of the element. But now when we go outside this from 100 mass of zeros, you have this weird stuff. That's what causes the it's all related to mass of zero. For them, you say that the almost structures are related in the mass of zero. And if you're in mass of zero, then you're just asking with this decomposition in feed one into the 001 is a decomposition of vector space. Because the modular structure acts as a co-unit, so it's just scaling. So you just need a decomposition of vector spaces. And so you have the same number of structures for the technical issues chain. One for the identification. Now when you come here, you've got this. You have to have a genuine modular structure of vector space. It's just not it's not a natural structure. And so that's where the decomposition of module is stronger than vector space, of course. That's going to be lower. So it's all connected to modules.
And question to the structure.
So on one side you had this finite dimensional part of the maximum prolongation perspective.
This one?
So those are the relations. So I was confused with these elements like E, gamma, E, beta, and so on. Are those in the finite dimensional part or elements?
What do you mean by finite dimensional part?
So if you apply topology, then you reach some finite dimensional vector space. And I was conclusive relations happen in this finite dimensional vector space. No.
I'm not sure what is your question. So for me, so for us, V1 is.
So maybe another question: what is this? What do you precisely mean by quantum exterior algebra?
Yeah. So this is gonna be. So you know our calculus looks like this. It's V1. So when we take the maximal prolongation of this differential calculus, we corresponding to this, that what we get is what we call the quantum exterior algebra.
Okay, so how I understand is that the maximum prolongation looks like a cotensor H.
Yeah.
But then I'm confused because in your setting you don't have a monoidal equivalence. So at least the part that I understand is if you're in a monoidal set, then this B bullet is an algebra, and then you apply the Takeuchi factor or its inverse, and then you get an algebra structure to maximum prolongation. But I think you don't need an algebra structure. Like you could just say this happens on the level of modules. So there's a off module, so you can decompose it in this way, and just what you get on the right side, this vector space is typically called the bullet, and then on top of that, I guess you figure out that there's some wedge structure on it, but the decomposition, I guess, happens on the level of modules first.
Yeah. You're correct. Okay, so basically
there is an monoidal structure going on because this thing can be lifted to a calculus, basically because of the calculus on the Hopf upstairs. You've got a monoidal structure, or a kind of something that looks like it. You've got a replacement almost. These things V are right A modules, and you can use that to get around the failure of the monoidal. I mean, yeah, it's a bit. I mean, basically that's why we think that replacing Takeuchi with this augmented one, where you don't have right.
got a writing. The algebra those the algebra structure, all of the components from the other and the pattern structure. But it's technical. Technical geometry instead of the sub.
Okay, there was another thing that this OQF3 doesn't admit a Kahler structure, and Raymond was expecting it, but it didn't happen. So yes.
It doesn't admit a metric in the sense of various machine because it's like so it looks like it's really a relatively simple example. Many things are working, and then many things aren't working. So it should provide the examples of when we see how to overcome these problems in depth. So are there any other questions or comments? I made one small comment myself. This example of these things are pretty. You're raising your hand. Is that this is all connected with the quantum BGG sequence for this quantum black manifold, and that was the thing that was used by Bob Youngkin and Christian Pollack from Planet conjecture for. Very probably didn't hear you.
Give me 1 second, Freddie. They used the BGG sequence for this, which should, in some sense, be dual to the complex that's going on here, that we don't quite understand yet. And so the higher analogues of this should hopefully have applications towards the quantum Baum-Kahn conjecture for quantum SUN or more generally quantum OQG. Freddie, do you have a question? Your hand is raised.
Yeah, my question is about this slide. So I'm also curious about these relations. So how did you get these relations for this full Fluck manifold?
So how did I get this? There are some computations. There is some, I mean, explicit there is an explicit formula you can find in the work of Ramon, and we just use that one. And nowadays, actually, we are trying to simplify that formula because to use that formula is not that easy task, even for this example. And we are trying to figure out something simpler, and then maybe we will attack OQFN at some point.
But how did you know that these are all the relations of the V bullet of the quantum extended algebra?
There is some, let's say, dimensional argument we have to use, and then yes. First we do computations, and then we do some dimensional argument to conclude that they are all.
Yeah. I mean, what you need to do is take a generating set for the classifying ideal of the calculus, and then you take you take a generating set, which you have to prove is a generating set, and then you take this map omega, the co-product by projection into the V1, tensor V1, and that gives you relations. And if the set of relations is a module, then that's all of the relations. So it's kind of technical.
Okay, yeah. So, and my second question is about the last slide. So you have pi, 2 pi.
Yeah.
In the theorem, what is pi?
It is 2 to the pi mean 2 to the power of number of simple roots.
The simple roots.
Yeah.
Okay.
So pi is the set of simple roots.
Okay.
So,
thank you.
Thank you very much for your question.
Yeah, very quick question. So what are the future plans? What is the next thing you want to prove?
For this one, I'm not particularly sure. Maybe we will try this conjecture at some point, but for that, we have to explicitly compute the maximal prolongation. And no?
Yes.
Yeah. Yeah. And that is a hard task with the existing theory. So we are trying to build something else, and then we will maybe use that formula to
some better machinery to calculate these in a more effective way. Yeah.
So at the moment, we are doing something else.
Okay, so if there are no more questions, question around 9, Junaid again.
Thank you very much.
Next week, we will have Next week, we'll have
Joseph van Dobbelen de Bruin, also from Charles University. And that will be just on the 18th of November. So see you.